show how light, not just electricity, is, well, powering huge parts of our world, often behind the scenes.
It really is a fundamental shift. People call it the century of the photon, and, there's a reason for that.
Okay.
Think about it. Light beams give us almost unlimited information capacity. We're talking terabits per second.
Terabits. Wow.
And maybe even more importantly, the losses are incredibly low, like less than zero point 0.2 decibels per kilometer in optical fiber.
And compared to copper.
Oh, vastly different. Copper's maybe 10 dBits per kilometer. The signal just fades so much faster. Plus, with light, you get no significant heat issues, and it's totally immune to EMI, electromagnetic interference, and crosstalk.
Right. No interference between lines.
Exactly, which means it's incredibly reliable.
So why did we make this, well, pretty radical shift? What gives light this huge advantage for sending data?
Well, these superpowers of light, as you might call them, let data travel, say, over 100 kilometers without needing regeneration.
Without boosting the signal.
Right, without converting it back to electricity, cleaning it up, and sending it out again. Copper needs that far, far more often. It's a massive difference in reach.
It's amazing.
And, the idea isn't entirely new. Alexander Graham Bell, back in 1880, he had this thing called the photophone.
The photophone, really?
Yeah, he actually sent speech about 200 meters using a beam of light. Visionary stuff, but way ahead of the technology needed to make it practical.
So Bell had the vision, but what were the hurdles? What finally unlocked modern optical communications?
Well, the big problems were getting light to travel long distances without losing too much strength, and generating that light reliably and efficiently.
Makes sense.
The breakthroughs really came in a few key areas. First, making ultra-pure glass for the fibers. That cut the losses way down.
Okay, the medium itself.
Exactly.
Yeah.
Then, developing reliable, efficient diode lasers to create the light signals, and optical amplifiers.
Amplifiers, like boosting the light directly.
Precisely. Things like EDFAs, erbium-doped fiber amplifiers, they boost the light as light without needing that electric conversion step. Huge deal.
And you mentioned bandwidth, too.
Right. That's where wavelength division multiplexing, or WDM, comes in. It's like sending multiple different colors of light down the same fiber simultaneously. Each color is its own data channel.
So you multiply the capacity of a single fiber.
Dramatically, yes.
Okay, let's dig into those laser diodes for a second. We know they're tiny, powerful. How exactly did they change things for storage and high-speed data?
Well, their size, power, and efficiency are just crucial. Blu-ray discs are a perfect example, actually.
How so?
A Blu-ray uses a blue-violet laser, around 405 nanometers. That's a much shorter wavelength than the red laser in DVDs, which is like 650 nanometers.
Shorter wavelength means?
It means you can focus the light onto a much smaller spot. That smaller spot lets you pack data way more densely, so you get, 25 or 50 gigabytes on a standard Blu-ray disc.
Wow. And I heard even more is possible.
Oh, yeah. Pioneer demonstrated putting 500 gigs on a disk with 20 layers. It shows this incredible precision we have with light.
That precision isn't just for disks, though, right? It applies to sending data, too.
Absolutely. That property, called coherence, where the light waves are all neat and aligned, and the ability to modulate them, basically switch them on and off billions of times per second.
Billions.
Billions. That's essential for firing these massive data streams through those long-haul optical fibers. It's the engine driving the internet backbone.
Okay, so lasers generate the data super fast. How does that light physically travel, say, across the Atlantic? How does it stay in the fiber?
It travels inside the optical fiber using a principle called total internal reflection. Basically, the light hits the boundary between the core and the outer layer, the cladding, at a shallow enough angle.
And just bounces back inside.
Exactly. It reflects perfectly back into the core, trapping the light and guiding it along the fiber, even around bends.
Are all fibers the same?
Not quite. There are two main kinds you hear about. Multi-mode fiber has a larger core. It's generally easier to connect, cheaper maybe, but the light can take slightly different paths inside.
Which causes problems.
Over distance, yeah. It causes something called dispersion fiber. The light pulse spreads out, blurring the signal. So multi-mode is more for shorter distances, like within a building or campus.
And the other type?
That's single-mode fiber, tiny core. So tiny light really only has one path to follow.
So no dispersion issue, or much less.
Much, much less. That's why single mode is absolutely essential for long-haul networks like those undersea cables, carrying huge amounts of data at high speeds, maximum signal integrity.
So connecting this back to the everyday, what does this intricate system of lasers and fibers mean for, you listening right now using the internet?
Well, think about the sheer scale. If you look at a map of undersea cables around Africa, for instance, you see these massive projects.
Like which ones?
Cables like Equiano, connecting Europe to South Africa, carrying something like 144 terabits per second. Or to Africa, aiming for 180 terabits per second, looping around the continent.
That's staggering capacity.
It is. These are literally highways made of light, connecting continents, powering cloud services, streaming, everything. Our global connectivity utterly depends on these light-based networks. The internet we use daily, it wouldn't work without them.
It really is incredible. From Bell's, well, almost science fiction idea with the photophone, to these globe-spanning networks carrying terabits on beams of light, the photon's journey has been pretty remarkable.
It really has. And it makes you wonder, doesn't it?
Sure.
Beyond just carrying our data faster and further, what other path, currently unlit, will light open up for us next? What haven't we even thought of yet?